Okay, this last video is about a little trick when looking at polynomials. There's a trick and it's related to the differences, the finite differences. And the finite differences are directly related to the leading coefficient of the polynomial. And we've already established that the leading coefficient of the polynomial is important in deciding end behavior, which gives it, we can identify like a sketch. Okay, so I'm just going to walk through this example with you and then show you the formula, show you the rule how this works, and you'll be expected to find the leading coefficient of a polynomial if we're given a table here. Okay, so let's first find the first differences. So the first differences, we're going to take 2, we'll subtract it by -3, we get 5. We're going to have 1 subtract 2, we get -1. 6 subtract 1, 29 subtract 6. We got 82 subtract 29. Oh, I gotta do that one. Okay, here we go. 82 subtract 29. Did you figure it out before me? 82 subtract 29. I get 53. All right. Now I'm gonna go 177 subtract 82. 95. Okay, so there's the first differences. They're not the same, so this is not a linear function. This is not a degree 1 polynomial. Okay. Second differences. Let's do second differences. All right, which is the differences of the first differences. So we got -1. We're going to subtract 5. That's -6. We're going to 5 subtract -1. So that's 5 plus 6. Or 5 plus 1. That's 6. 23 subtract 5 is 18. 53 subtract 23 is 30. And 95 subtract 53 is 42. All right, now, so the second differences are not equal, which means this is not a quadratic relationship. And the idea here is if the third differences are equal, then this is a cubic. If they weren't, then we'll check again. And if the fourth differences are equal, then it's a degree 4 polynomial. And this is always the case. If you have a table of values and the nth differences are equal, then this is a degree n polynomial. So let's try the third differences and see what we get. Third difference. Okay, so we got 6 subtract -6, that's 12. We got 18 subtract, so that's 12. Wait, 12. That's 12. Good, so all the third differences are equal, which means this is a degree 3 poly. Okay, so this is a cubic. We don't know what the equation looks like, but it will look something like x cubed, a x cubed, and so on, so on, so on. But we can find a little more about this because the value of the differences themselves are related to the first term, the leading coefficient, and they are in this way. If the nth differences are equal to, now I want you to copy this down, the nth differences are equal to this calculation where A is the value of the leading coefficient. Okay, now how we read this is, say, we know that it's 12, so 12 must equal this calculation. 12 must equal A times, now n is the degree, okay, so the value of the degree. So this is like 3 times 1 less than that times 1 less than that times 1, all the way down. Okay, so if you had like a degree 10 polynomial, this would be A times 10 times 9 times 8 times 7, all the way down. Okay, so what we have here is the nth differences, which are 12. So 12 must equal A times. We've already know that this is a degree 3 polynomial, and n is the degree number. So this is 3 times 1 less than that. What's n minus 1? So that's times 2 times 1 less than that. That's 1, and we stop. We always stop at 1. Okay, so we've got 12 must equal A times 3 times 2 times 1. That's 6. So 12 must equal A times 6. Let's solve for A. A's got to be 2. So we've got a positive leading coefficient. Its value is 2, and we know it's a degree 3 polynomial. Okay, so now we can determine what the end behavior of this is. Since it's a degree 3 polynomial and it's odd, we got something that looks like this. Let me do a quick sketch here. So it's something that looks like it's got M behavior going up this way and then down this way and something going on in the middle. Okay? So that's a question like that. We should be able to determine the degree or the leading coefficient if I'm given a table of values of any polynomial.